Greetings! Welcome to Electronics2. This is lecture number 27 and I am Razavi. Today we will start a new topic, namely feedback, and begin to introduce the concept and understand what it means and why it's interesting and useful. In particular, after some introductory remarks, I will show you the general feedback system and identify its various components. And then I will derive what we call the closed loop transfer function, which carries a wealth of information for us in terms of the properties of the negative feedback system and the benefits and the disadvantages that it might have. So, what do we mean by negative feedback? Well, feedback has been around for as long as humans have been around. Actually, as long as dinosaurs have been around. Well, they're not around, but just as an example, close your eyes and try to touch your fingertips. Okay, so if I look away and I try to touch, I can't. Why? Well, because I have broken a feedback loop consisting of my eyes and various other parts that monitors the movement of my fingers to make sure that the fingertips touch. Okay, so the notion of having a loop that regulates and monitors movements and actions is very powerful, and you can see that that can happen in biological systems, engineering systems, many different systems. So let me give some more examples of negative feedback to see how it plays a role in everything that we do. So examples of negative feedback. Well, our eyes. Our eyes have feedback in them. How so? Well, remember what happens when you go from a dark room to a bright room. The pupil, the size of the pupil shrinks. Why? Because we want to allow less light into our eye, right? So pupil shrinks when we go to a bright room. So the eye is smart enough to adjust the size of the pupil to make sure that the amount of light that enters our eye and hits the retina in the back is controlled, right? That's the negative feedback system. Another one is our ear. So here's our ear. So ear. You might have experienced this. If you go to a concert that has very loud music and you stay there for 1 or 2 hours, and then you leave the concert and you go to a quiet area, you feel like your ears are a little deaf. It's like you are a little hard of hearing. Why? Well, what happens is that when the music is so loud, the ear has a mechanism to adjust the threshold of hearing so that that loud music does not significantly affect or damage your hearing. So now when you leave the concert, that mechanism is still keeping the threshold at that point, so you feel a little hard of hearing. And it takes some time for the ear to go back to where it was. So again, that's the negative feedback system that tries to adjust the volume of the level of the sound that enters your ear. Okay, so we have these everywhere. And it's the amount of control that they provide, the regulation that they provide is extremely useful for our actions. All right, so now, in practice, of course, we have feedback in our circuits and in many other applications. So what do we use feedback for exactly, right? And these were something that we have in biology, but in practice, how do we do that? So we ask this question, why negative feedback, right? So for example, in circuits, what am I trying to achieve? Or in mechanical engineering, why do I need negative feedback? Well, okay, so let's start with a simple example. Let's build a simple common emitter stage. V in here, V out here, and a load resistance RC. Now we know that the voltage gain of the circuit, if the early effect is neglected, is equal to minus GM times RC from Electronics 1. All right, now the problem with this is that the voltage gain is not very accurate. It can vary quite a bit. Why? Well, for example, this resistor, however we build it, on a chip or as a discrete resistor, has some variability. With temperature it changes, from sample to sample it changes, so it's never that accurate. So for example, if an application requires a gain of 4.00 to such precision, there's no way that this can give us that amount of accuracy. Okay? So we have many examples. There are many interesting circuits that do need such a precision, and for those we can't use something like this, right? It just wouldn't work. All right, another example. So in mechanical engineering. Okay, so here's a slope, a road, and we have a car on this road, okay? Like so. So we have a car that's going down. And if we just let the car go by itself, the speed will keep increasing and increasing, right? There's no way to control the speed. The slope wants to accelerate the car, the speed keeps increasing. So without any feedback present, we have no control over this car. So what we say is that without feedback, we have what we call untamed. Untamed means like wild. Untamed and poorly controlled circuits and systems. Okay, so that's the trouble, right? We have variability in the gain of the circuit, that's a poorly controlled gain, and we have the speed that is not controlled, so because we have applied no feedback. So the point of applying negative feedback is to see if we can make this gain better controlled. It's a tighter gain definition so that it can stay around 4.0, for example, right? And similarly, the purpose of applying feedback here would be to make sure that the speed of this car is some amount that we want. So let's say 65 miles per hour, 100 kilometers per hour, or something like that, right? So that would determine the speed and would keep it approximately at that speed. All right. So that's why we need negative feedback in many applications. And in fact, we have seen negative feedback in circuits before, but we didn't really call it feedback. So here are some examples. So we have seen negative feedback before in Electronics 1. So remember the non-inverting amplifier using an op-amp? That is actually a negative feedback system, as we will see later. The inverting amplifier, like so, that's another negative feedback system. And the integrator, as we saw before, is also a negative feedback system. Okay, so all of the circuits use feedback to their benefit. Without feedback, it would be much more difficult to obtain the nice properties that these circuits offer. And it is feedback that helps us build these with a certain level of precision. So again, we will return to these after we have learned feedback and we have studied its properties. All right. So in the spirit of controlling things and making things more accurate, let's just go ahead and see how we could build a negative feedback system for this car. Now, we don't know what feedback is really. We don't know what negative feedback system should look like. That's okay. We're just contemplating. We're just thinking, what would it be like to try to control the speed of this car? So we're trying to build a cruise control system, right? That's how we adjust and control the speed. So let's try to build. Let's build a cruise control system. All right. Based on what we know, again, we're not looking for something fancy and very accurate and very realistic. We just want to put a few things together and see if somehow we can control and regulate the speed of a car like this, right? All right, so here's the car. And this car has an engine. Obviously, we have to work on the engine, right? And it has a speedometer, so it can measure the speed. So there's a speedometer right here. So we'll put the speedometer out here. Speedometer. And we assume that the speedometer is measuring the speed of the car as the car is moving, right? And the speedometer has an output voltage, and that's true. And the speedometer does have an output voltage. So there's a voltage here, so we'll call that VSP, the speedometer voltage. And what we know is that the faster the car goes, the higher this voltage will be. So in other words, for the speedometer, we have some sort of characteristic like this. VSP as a function of speed. It's like this, right? Approximately speaking, very roughly speaking. So the higher the speed, the higher the voltage. All right? Okay. So my objective is to make sure that even though I'm driving on a slope, the speed of this car is a certain amount. So let's say 65 miles per hour. So if the speed of the car is a certain amount, so let's say 65 miles per hour, then the voltage coming out of the speedometer is known. So let's call that V1. For example, 500 millivolts, right? Just an example. So what I know is that if the voltage from the speedometer is 500 millivolts, then the speed is 65 miles per hour. I'm good to go. So what I want to do is continue to look at the voltage at the output of the speedometer right here. monitor it and make sure that I adjust the speed of the car so that this is always in the vicinity of 500 millivolts, right? Now, how do I do that? Okay, so I'm going to take a battery that has a voltage of 500 millivolts. So 500 millivolts. This is my reference point, my reference voltage, right? And I need to make sure that this voltage is very close to this voltage at all times. So somehow I have to measure these two against each other, right? So maybe just subtract them from each other, right? If they are very close, the difference should be very small. How do I subtract two voltages? I have op amps. Op amps can do that, right? So I'll take an op amp and hook it up like this. And I place a negative sign here, positive sign here. So far, so good? Okay, so what I managed to do at the output of the op amp is generate a voltage quantity that is proportional to the difference between these two with a negative sign. All right, now I'm going to take that. So let's change the color to this one. I'll take this and bring it and apply to the engine. Of course, the op amp itself cannot directly drive the engine. It has to go through some more stages and so forth before it can reach the engine. But conceptually, let's see that's what we do. Okay, so now what happens? All right, well, let's suppose that the car is on a slope and wants to speed up. So it wants to go beyond 65 miles per hour. If it goes beyond 65 miles per hour, this voltage wants to go above 500 millivolts. If this voltage wants to go above 500 millivolts, above this one, the op amp says the inverting input is higher than the non-inverting input. So this voltage has to go down, right? If this voltage goes up, if this difference goes up, this has to go down. This voltage goes down. If this voltage goes down, the engine slows down, so the car goes more slowly. And conversely, if for some reason, let's say we're going up a slope, the car wants to go slowly, then this voltage will be less than 500 millivolts because we're over here. If the voltage is less than 500 millivolts, this voltage wants to go up. If this voltage goes up, the engine wants to go faster, so we go back to 65 miles per hour. So you can see that there's a loop here consisting of the car, the engine, the speedometer, this amplifier, and this line that comes back to the engine, trying to make sure that the speed of the car is relatively constant, even though we might be going up a slope or down a slope. All right, this is an example of a negative feedback system. Now, of course, we have to formalize our understanding of such a system. We have to identify its components carefully and properly, but this just gives us a feel for what we are looking for. All right, very good. So let's go ahead and introduce the general feedback system. So general negative feedback system. All right, well, we are sort of concerned about circuits, of course. What we introduce here is more general. It can be applied to any systems. It doesn't have to be even electrical. But let's just take a step back and remember our circuit problem, right? Our circuit problem was that I bought an amplifier, and the voltage gain of the amplifier is not very precise. It's not very well controlled. So let's model this amplifier by a block here. We call it A1. So I bought this amplifier, and I brought it here. Ordinarily, my input would go here, and my output would be here, right? Okay. All right. Now, I would like to exploit negative feedback to improve the accuracy of the gain of this amplifier. All right. So this is what we will do. We say, okay, we will take the output, pass it through something else, which we call the feedback network. Okay, this is called the feedback network. And we will bring it over here, and we will subtract this result from the input. And then the result goes to A1. So, the input, the main input of the system, does not go directly to the input of the amplifier, like here, right? Instead, because I'm trying to build a better amplifier, I have immersed that amplifier inside this big system, and I have applied my input over here. The output is still here. The output is still taken from the amplifier, but the input goes here. So this is a general negative feedback system. It has many interesting properties. We will look at it very, very carefully as time goes by. Okay, so don't worry. It might be a little abstract here, but not a problem. We'll get there. Okay, so what we can see is that a negative feedback system requires 4 components. So let me identify those components here, and then we go forward. All right, so the first component is this one. Well, this A1, which we call that the feed forward system. It's just a name, don't worry about it, but obviously we have to have that, right? That was the untamed, the poorly controlled system, the poorly controlled circuit. So obviously we have that, and we're trying to improve it. So obviously we have that. Okay, the second component we need is a sensing mechanism. A sensing mechanism for the output right here. Okay, so right now we don't see any sensing mechanism. It looks like a wire, but here the sensing mechanism was the speedometer, right? The speedometer was measuring the speed. The speed was the quantity that we were trying to regulate. So we need a sensing mechanism. The third component is the feedback network. So the third component is the feedback network. Now at this point we don't know why we have a feedback network. That's okay, we'll get there. So we just have it. And the fourth component is this little guy here. What is this? Well, we call this a comparison mechanism. It's comparing this signal with this signal, right? Let me name this U. So we'll call this U. It's comparing X and U. In particular, it's subtracting U from X. So we'll call this a subtractor. Okay, it's really comparing the two, right? We call it subtractors. All right, so some terminology, some definitions, just to make sure that everything is clear. All right, so the signal that appears here has a name. We call this the feedback signal. Okay? What appears here, we call it the error signal. All right. Okay. So you can see that the error signal is just X minus U, right? Because that's what the subtractor does. So that's X minus U. All right, one more definition. This feedback network, it might be really complicated or really simple, but all it does in most applications is this. It takes this output, this Y, and just multiplies it by a number. That's all. So that number would be K, would be denoted by K, and K, so here U is equal to K times Y. That's all it does. And this K has a name. So K is called the feedback factor. Okay, feedback factor. Feedback factor means by what factor do we multiply the output to generate the feedback signal. Now, some books denote the feedback factor by beta, but we don't, because beta is also used for the current gain of bipolar transistors. So then there will be confusion, right? So we just use uppercase K for the feedback factor. All right, so this is the general picture of a negative feedback system. We don't quite know how it works, we don't quite know what it does, but at least we have identified the different pieces that we need here. Do all of these map to what we have here? If this is a negative feedback system, can I identify everything here? More or less. What is the forward system? The feed-forward system. It's the poorly controlled system that we wanted to regulate. That's the car, right? That's the car plus the engine. So that's the feed-forward system. The sensing mechanism is the speedometer. It's measuring the speed of this car. The feedback network. The feedback network is what? The feedback network is nothing really, just a wire, because we sense and we bring it over here, right? We don't really have a feedback network, just a wire. The subtraction, the subtractor. The op-amp is doing the subtraction, right? They subtract these two. And then the result goes back to the system under system of interest, which goes back to the engine. So roughly speaking, we have everything that we see here as well. All right? Okay, very good. Let's continue. I would like to make some notes, additional notes about the system. So let me go to the next slide here. And see what we know. Okay, so notes. And I will draw it again here because we need this all the time. So X goes in, gets subtracted, what U is subtracted from that, this factor of K, A1 for the feed-forward system, and this is Y, right? All right, so number one, we have negative feedback. Negative feedback. So how do we know this is negative, not positive, right? Well, that is this sign here. Okay, because U is subtracted from X, we call this negative feedback. Now, there's another deeper understanding that we should address later, but for now, that's all we care about, okay? We say because the feedback signal is subtracted from the input, we say this is negative feedback. All right, number two, a direction of signal flow. Okay, so there's an implicit assumption here, and we just need to be aware of that and remember that in the future. The assumption is that there's a signal going through A1 this way, and then coming back through the feedback network this way, and then getting subtracted from X. So in a sense, we're assuming that the signal is flowing in this direction, right? We're not assuming any signal to go this way, and that way, right? So it seems pretty obvious that it should be like this here, but when we get to circuits, sometimes it's a little more confusing. So we just have to remember that the directional signal flow is this way, right? All right, just to make sure that we have everything well defined and clear in our head. All right, next we have the error signal. As I said before, the error signal is X minus U. Why do we call this error? It seems that it's unwanted, that's why we call it error, and it's true. So as we will see, we want to minimize this error. So must be minimized. And of course the question is how and why, right? How and why, or why and how. Okay, these are questions that we will have to answer later. But this error here, so that's X minus U, right? We want to minimize this error here, so we'll have to see why and how. Okay, Next point. The next point that I would like to raise is the following. All right, so we have two other definitions, what we call the open loop system and then the closed loop system. So both of these come into picture all of the time when we are studying feedback systems. So we have to have a very clear understanding of what we mean by the open loop system and by the closed loop system. All right? And again, that can be confusing, especially for the open loop system. So let's try to make that, give it a simple condition that's always easy to satisfy. All right, so open loop system means K is equal to 0, and closed loop system means K is not equal to 0. So let's try to draw the circuit when K is 0. Okay, what does it look like? Okay, K equals 0 means that U is 0 because U is equal to K times Y. It means nothing comes back here, right? So we have killed the feedback. The feedback is non-existent. So what this means is that you can have this, you can have this, you can have this, but nothing comes back here. So we'll ground this. This is 0, right? You agree that this would be the same as when this is 0, right? If K is 0. Whether this K is 0 or not, because it's not going anywhere, it's like the system is open. So we call this the open loop system. In this case, you can see that, in fact, what we have is this is 0 subtracted from X. So this is just X, and this is just Y. So the open loop system is really just like that original amplifier that we bought, the untamed, poorly controlled system or circuit. So just that, right? Okay. The closed loop system, on the other hand, is the entire system, right? So we have everything in there. Everything is moving along and working as expected. So that is the closed loop system, X and Y. Now, it is tempting to say that the open loop system, if I look at this very carefully, is equivalent to just A1, right? Because if this is just X minus 0 going in here, that's just X, this is just Y, this doesn't do anything, this doesn't do anything, so it's just A1, right? And in many cases, that's true. When we say open loop system, you can get rid of everything else and just consider the basic untamed amplifier that we bought. But there are some minor, some subtle cases where that's not easy to do. So for now, if you want to think of the open loop system as just the original amplifier, the feed-forward amplifier or system, that's okay, but we will see that sometimes it's not as easy. All right? Okay, so that's the open loop system. This is the closed loop system. All right, let's see. Okay, so let's try to find the transfer function of the closed loop system. So transfer function of closed loop system. All right, so I'll draw that again because we need it. And transfer function simply means y over x, right? So we would like to see what we get in this case. So y over x. That's what we would like to find. All right, so when I bought the amplifier, just for the amplifier, so for the open loop system, y over x was just A1. It was simple, right? But now I have placed this amplifier inside a feedback loop. So presumably y over x is no longer equal to A1. If it were, then we would be back to square one. They would still have a poorly controlled amplifier. It wouldn't be useful. All right, so how do we go about doing that? Well, if this is y, how much is u? the feedback signal? The U is given by K times Y, right? So K times Y, we said that's all this network does. It takes the signal at this point, multiplies it by K, and generates it here. Then how much is the error signal? The error signal is X minus U. So the error signal is X minus U, so X minus K times Y. Okay, so here we have X minus KY. And what does this do? This amplifier says, I multiply my input by A1 to produce the output. So Y is equal to A1 times X minus KY. So now we can find Y over X, right? So you can see that Y over X. So we have A1X on one side, and then we bring this to the other side, we have Y times 1 plus KA1. So that becomes A1 over 1 plus KA1. This equation is the most beautiful equation in feedback systems. This equation tells us so much about negative feedback, and in fact actually positive feedback too, but our study is only negative feedback. We will examine this equation from many different perspectives, and we will see so many beautiful properties that come from negative feedback as a result of this equation. Okay, so you do need to memorize this equation for the rest of your life. All right. Okay, so that says that the closed loop gain, for example, is some amount. The open loop gain was A1. The closed loop gain is A1 over 1 plus A1, KA1. So again, let's have some terminology here. A1 is the open loop gain, and A1 over 1 plus KA1 is the closed loop gain. A1 is just the gain of the amplifier itself, right? The amplifier that we bought. But now that we placed the negative feedback loop, the overall gain came out to be like this. We call this the closed loop gain, right? After the loop is closed around A1, the overall function from X to Y gives us this much gain. Okay, all right, so now that we have these, one thing we can observe is this, that we assume that K and A1 themselves are positive. Okay, so K and A1 are positive. So the negative feedback is reflected in sign, and the assumption is that A1 and K both are positive. So now what we see is that this number is less than A1, right? Because we're multiplying by 1 plus some positive number. So what we see is that the closed loop gain is always less than the open loop gain. So naturally you ask why? Why do we do this? Right? Why are we deliberately reducing the gain? So why do we reduce the gain? Okay, that's the question that we'll have to answer later. Okay, we don't have an answer yet, but once we look at the benefits of negative feedback, we will see that the reduction of the gain is very well justified. Okay, so there are some other questions that we will also encounter, so we should write them here. How do we implement the subtractor this subtractor that we talked about, right? The subtractor here. How do we exactly implement this if you are designing circuits? In other words, how do I subtract two quantities? I can subtract two voltages, I can subtract two currents or other parameters of the same dimension. So how do we do that exactly? In the cruise control example, we saw that we subtracted two voltages using an op-amp. So that's a good candidate, we should remember that, but generally we'll have to answer this question later. And finally, the other question that we have is, what is the purpose of the feedback network? Right, this K. What is this doing here exactly? Why can't I just take this wire and bring it directly to here? Why do I have to go through something before I get here, right? So these are still not clear in our mind, and as we go along and as we discover these interesting properties of negative feedback systems, we will see why the feedback network is necessary. All right, so that was the closed loop transfer function of this system. All right, let me give you a quiz here. Determine the error signal in terms of the input X, right? So in other words, we're looking for this value here in terms of X. We found Y in terms of X. Y in terms of X is that, right? So what is this error in terms of X? I'll give you 1 minute to think about it. All right, so what did you get? Okay, well, we remember that the error signal is equal to X minus U, right? So X minus U gives us this error signal, and U is K times Y. So it's equal to X minus K times Y, and we know Y in terms of X. Y is this times X. So that would be equal to X minus K A1 over 1 plus A1, K A1, right? Okay, so we times X. So we simplify these, and we see that this K A1 goes away with this K A1. We have X over 1 plus K A1. So that's the amount of error that we produce at this point. And as I said, we will see in the future that one of our objectives is to minimize this error. And to minimize the error, we have to maximize this quantity here, right? We don't have any other option. X is the input. We just want the error to be very small, so we have to maximize this quantity. And we will see that this quantity plays a profound role in the performance of this overall system. Okay, so, but from this emerges an observation, which is interesting. So as we try to maximize Ka1 so that the error is minimized, we can see that the X and U become approximately equal, right? So observation if the error is minimized, we don't know why, right, yet. if the error is minimized, then x minus u becomes small, which means x and u become approximately equal, right? So that means that the feedback signal u becomes very similar to x, to the input signal. So if this is x as a function of time, then u, the feedback signal, will be also very close, right? So u will also be close. So that would be u. So that means that the feedback signal is a good copy of the input. Right? U becomes a good copy of x. And that's also a critical point in analyzing feedback systems. All right, we will encounter this many times, but this is the net result that we get, that when the error is minimized, x and u are very close to each other, so we can say that the feedback signal is a good copy or a good replica of the input signal. So we'll come back to this many times in the future. All right, this concludes our lecture today. And as you can see, we have just barely touched negative feedback systems. There's so much to learn, so much to discover about this transfer function, about these properties, and so on. And we'll just take our time, and every time we'll go deeper and deeper. I will see you next time.